talking about when you want to form the material or matter from atoms. There are two types of forces that exert on the atoms and molecules. Okay, one is called intramolecular forces, which is going to give the intramolecular bonding. So this process is the force that kept molecules together within the molecules. So you have this atom A, you have this atom B. So to form this molecule, you have intramolecular bonding. Okay. The second one is intermolecular forces. Form the intermolecular bonding. So it's the attractive forces between molecules which are responsible for keeping in their form, whether it's the solid or liquid phases. Okay. So you see here you have the molecule. Okay, and it forms larger molecule here, and this is the similar larger molecule. So between this molecule there are secondary forces between it, and this one we call it the intermolecular forces that form the intermolecular bonding between the molecules. About the intramolecular bonding, or we call it the primary bonding, that bond together the atoms within the molecule. We have three types of this bonding, which is one is we call it ionic bonding, another one we call the covalent bonding, and third one we have the metallic bonding. However, for the intermolecular bonding, it's between the molecule. When we have the secondary bonding, or we call it van der Waals bonding. So we can find van der Waals bonding between the molecules. One, we have fluctuating induced dipole, polar induced dipole, or permanent dipole. For example, hydrogen bonding. Let's move to the ionic bonding. Okay, as I mentioned before, it is the bonding where it forms strong electrostatic attraction between two oppositely charged atoms or molecules. It can have positive or negative charges. So it's found when a compound or the molecules are composed of both metallic and non-metallic elements. So you can check whether it is metallic or non-metallic elements in the periodic table. So normally atoms are neutral, okay? As we normally assume that when we refer atom, it's normally neutral. But to gain stability, they have to either losing or gain electrons. Because previously I mentioned most of the atoms in the periodic table is not stable. Only the inert gases are the stable atoms which already reach the octet. So when atom losing one or more valence electron, which is at the outermost shell, is going to form positive charged ions called as cation. If the atom gain or receive electron or more valence electrons, is going to form negative charged ions or called as anions. So due to its electronegativity, the tendency to accept the electrons from other atoms, metal elements tend to lose electrons. The metal elements or the metallic atom has highly electropositivity, means that it has low electronegativity. Meanwhile, the non-metallic elements tend to gain electrons and is highly electronegative. So when one of the atoms losing electron, one other atom receiving the electron, it becomes ion. So these ions, positive and negative ions, is going to attract to each other to form the ionic bonding. However, the ionic bonding is non-directional. It does not have a direction because the bonding that forms between the ions is equal in all directions. So here I show you the periodic table of the elements, and we are talking about the electronegativity, right? In order to know whether the material or the atom have tendency to accept or to give up electrons. So from this periodic table, you see when from the top to bottom, experience decreasing in the electronegativity. Meanwhile, from the left to right, experience increasing in electronegativity. So this is few example of the ionic material. One is the simplest example, which is sodium chloride. Okay, so you see you have the sodium here, which is the metallic atom, with the chlorine here, the non-metallic atom. So whenever you want to represent how ionic bonding is formed, so here we see one example, which is NaCl, where you have sodium that is equal to 11. So it has 11 electrons, and from that that you know it has 1 electron valence. Meanwhile, for the chlorine, it has that value of 17, so the electron is 17. So it has 7 electron valence. This one needs another electron to achieve octet. This one needs to receive electron in order to reach the octet. So from that, you know, when the sodium atom losing the electron, which is 1 electron, okay, so it forms cation. Meanwhile, chloride atom form chloride ion, okay. So you have to show that it transforms from atom to ion, okay. Because could be there are questions that need you to draw the reaction between the atoms in order to form the bonding. So you need to show the transformation from atoms to ions, and then the ions become closer together to form the sodium chloride. So this one is the ionic bonding. So the opposite charges attract and the ions form sodium chloride. So there are electrostatic attraction between oppositely charged ions and called ionic bonding. So these are the general properties of the ionic compound formed from the atoms which have higher electronegativity plus lower electronegativity that forms ions and then attracted to each other via the strong electrostatic charges. So you see, due to this strong electrostatic attraction between the atoms, the material or the compound always have high melting temperature and evaporation point. Okay, so why it has high melting temperature? Because the bonding energy is relatively large. Previously, we know that the bonding energy, the E node high, so you have high melting temperature in between the 600 to 1500 kilojoule per mole. And then the material is usually hard and brittle at room temperature. Why is hard and brittle? So you see here, one example is to show you how when you have different ions, positive and negative ions, when subjected to forces, okay, and stresses, okay, you see the ions is going to slide over another. The ions which have similar charges will start to repel between each other. So this little faster forces going to introduce fracture or crack within the material. So that's why it's brittle. It needs more energy in order for it to break the bond. So it's hard, but when it started to move, it suddenly fractures. So it's brittle. So it does not conduct electricity, okay, even though it has positive or negative charge, but it is not conduct electricity because positive and the negative charge of the both ions neutralizing each other, except if it's been in the molten state or when it's dissolved in water. Ionic compounds can conduct electricity when their ions are free to move. Say for example, when we have table salt, sodium chloride, it can conduct electric when dissolved in water, and the ionic compounds are mostly water soluble. Now we move to covalent bonding. So the covalent bonding is the second primary bonding for materials. It's actually formed when two or more elements sharing their electrons. So the key point for this covalent bonding is sharing. Okay, so it occurs because the atoms in the compound having similar tendency to gain electrons, and it commonly occurs in two non-metals bound together. Okay, so can we refresh our memory? As mentioned previously, most of the metal having high electropositivity, meanwhile non-metal have high electronegativity. So electronegativity is the tendency for the atom to attract electrons from other atoms. So now when you have almost similar atoms which having almost similar electronegativity, so it is tend to share rather than to give up or to receive electrons in order to form the material. So one is occur when you have two non-metals bound together, such as the chlorine gas, hydrogen gas, fluorine gas, and so on, where you have both similar atoms, Cl with Cl, like this one, Cl with Cl. Or you can have covalent bonding when molecules containing dissimilar atoms, like methane when you have carbon and hydrogen, nitric acid when you have hydrogen, nitrogen, and oxygen, as well as water when you have hydrogen atom as well as oxygen atom. So covalent molecules tend to exist as liquid or gaseous at room temperature. This covalent bonding is directional because it has specific atoms in the direction between one atom and another that participates in the electron sharing. There are two types of covalent bonding, which one is polar bond, another one is non-polar bonding. So polar bonding, when the electrons between the atoms are not equally shared. For example, it happens in the chloric acid, water, phosphorus trichloride, and ammonium. So you see here, this is one example of the polar bonding for water. Due to the electronegativity of oxygen, which is larger than the hydrogen, electron is having tendency to spend more time closer to oxygen rather than with hydrogen. So it forms dipole moment. The second is non-polar bond, actually formed when there are equal attractions from electrons. So you see, this is one example of the non-polar bond for carbon dioxide, chlorine gas, or methane. So you have this carbon and oxygen. Because of the almost similar electronegativity, even though it has slightly positive or negative charges, but it is neutralized between each other. The dipole moment is cancelling each other, so it becomes non-polar bond. Another example of covalent bond, for example, for single and polar bonding. Here we have chloric acid. So you see, for the hydrogen atom, it has 1 electron valence, whereas for the chlorine atom, it has 7 electron valence. So each chlorine share 1 electron, and hydrogen also share 1 electron in order for both of it to achieve octet. So it forms covalent bonding via single bonding between these two atoms. You have H2Cl. So this one is single bond. However, since according to the electronegativity of hydrogen and chlorine, the chlorine having higher electronegativity, so electrons that been shared together spend almost all their time around the chlorine atom rather than around hydrogen atom. So because of that, there are dipole moments formed in between the hydrogen and chlorine. That's why chloric acid having polar covalent bond. Now we look another example for the single bond but non-polar. There's no polarity between the atoms when it forms covalent bonding. So it happens in the chlorine gas between two similar chlorine atoms. So you see here, both chlorine atoms need to have only 1 electron in order to reach octet. So each of the atoms will share 1 of their electrons to be stable. So it forms a single bond. Okay. Since the electronegativity between chlorine is the same, so neither atom claims more share of the pair of electrons, so they spend equal time around each other, so it's producing non-polar bonding. We have seen the example of acid hydrochloric, where the combination between hydrogen plus chlorine will produce polar covalent bonding, meanwhile the chlorine gas producing non-polar. But here we want to see another example of methane, where actually methane produces single bond but non-polar. Okay, so you see the methane involves two different atoms, which hydrogen and carbon. Okay, so from the electron valence, when you do all the electronic configuration, you will find out that hydrogen only have 1 electron valence, meanwhile carbon has 4 electron valence, right, at the valence shell. So for hydrogen, it only needs another 1 to reach octet. Meanwhile, carbon needs 4 to reach octet. So in order to form methane, carbon needs to form or sharing the electron with 4 hydrogen, okay, in order to become stable. So it forms the covalent bonds with 4 hydrogen atoms to produce methane. You see here, the electronegativity of hydrogen is 2.1, whereas the carbon is 2.5. So it means that the carbon part will be having slightly negative charge, since electron will have tendency to spend more time with carbon atom rather than the hydrogen atom. So the hydrogen atom will be slightly positive charge. So why in this case it becomes non-polar? The reason why covalent bond become non-polar, it can be due to, one is because of the almost no polarity, okay, as we observe in the chlorine gas. But another reason is due to the symmetrical arrangement of polar bonding. So in the case of methane, the 4 CH bonds are arranged tetrahedrally around the carbon atom. So the bonding are arranged symmetrically. So there is no dipole in the molecule. So you see here, you have carbon, which is slightly negative. You have hydrogen, which is slightly positive. But due to the dipole moment, which cancelling each other, so there is no net dipole moment for methane. So it produces covalent non-polar bonding between the atoms. When each pair of electrons between two atoms are shared, a single bond will actually form. Okay, but some of the atoms can share multiple pair of electrons, more than one electron being shared between the atoms. So this will form multiple covalent bonding, whether it is double bonding or double bond or triple bond, and this is what we call unsaturated bonding. Okay, so this unsaturated bonding or the multiple covalent bonding is mostly non-polar because the electron actually been shared equally between the two atoms, or even the dipole moment within the atom is cancelling each other to become non-polar. These are the list of the general properties for covalent compound. It divided into two, whether you have covalent solid or you have substances with covalent bonding. So there are major difference between these two solids, because if you have a system having both intra and intermolecular bonding is by covalent bonding, such as seen in the diamond. Okay, here is the structure. You see at this particular carbon atom, it is from covalent bonding, boron nitrate or quartz, silicon nitrate or silicon carbide, mostly shown non-conductive in solid and molten state because no free electrons and ions. So this material not be able to conduct electricity. Okay, most of it also having very high melting temperature, and definitely it is not volatile. So it able to be used for high temperature application, but due to the high melting temperature, it is also hard to produce covalent compound to form product in the manufacturing. Also, the processing temperature will be high. The covalent compound, due to the directional behavior, it is very strong and hard. It is insoluble. Okay, because it needs very high energy in order for it to break the bond between the atoms. But if the covalent bonding form within the substances, which is a form at the intermolecular level, here, this is one example of this material for graphite, where actually the covalent bond is between the atoms at the plane, but there are a distance separating the layer of the graphite via secondary bonding. So this kind of covalent compound having low melting and boiling temperature, and it's soft in solid. Solubility depends on the polarity of the molecules. An example is the graphite here, you see, and also the polymer. Because polymer is mostly hydrocarbon, right? So between hydrogen and carbon, it has intramolecular bonding by covalent bond. But between the chain of polymer, it involves weaker bonding, which is van der Waals. Actually, it is very hard to find a compound which exhibits pure ionic or covalent bonding. In most cases, the compound having partially ionic or partially covalent. So for this material, whether it is more towards ionic or more towards covalent is based on its difference in the electronegativity between the atoms. If the difference of the electronegativity is high, so it has greater tendency to become ionic bonding. Whereas if the atoms are closer together in the periodic table or having smaller difference in the electronegativity, it has greater the degree of covalency. So we can calculate the percent of ionic character using this simple equation. The third type, primary bonding, is called metallic bonding. It's found in metal and its alloy. Okay, for this type of metal and alloy, the valence electron is not shared and not bound to any of the particular atom in the solid, and it forms sea of electron or electron cloud. So as you can see here, this is all the electron valence in the electron cloud. The remaining electron, because you know that you have the nucleus, right? So you have other electrons at the lower energy state closer to the nucleus, and then you have the electron valence. This electron valence will form the electron cloud, but both the remaining electron plus the nucleus of the atom will form the ion core that having net positive charge. So this electron cloud and the positive ion core is forming the attraction forces between each other, forming a very strong metallic bonding. So the electron valence will act as the glue between the positive ion core. Okay, you can also represent the metallic bonding this way, where actually this one represents the positive ion core and this the negative is representing the electron cloud. Here is the general properties for metals and its alloys. So first, you can see that bonding energy between metals and alloy is in the range of weak to strong. Okay, there are metals which having very low bonding energy at only 68 kJ per mole, which is for mercury, and you can also have very high bonding energy for tungsten, which is about 850 kJ. So due to this bonding energy, you can find metal having the range of high melting and boiling temperature from the -39 up to the 3,510 degrees centigrade for tungsten. Due to the presence of electron cloud within the metal or alloy, metal are good conductor for both electricity and heat. So you see here, you have this positive ion core, and then you have this free electrons. Whenever you apply the voltage, the difference in the voltage cause the electron to having the drift velocity to creating current. That is why metal and alloys are good conductor. Another thing is metal and alloy is insoluble in all solvents, and then it has good ductility, and most metals and alloys workability is easily to be shaped, and it is been subjected to forces. Most of the time when the force surpasses the strength of the metal, it's going to fail in the ductile manner. The fracture is going to occur whenever the material already experience a degree of permanent deformation. So this is due to the formation of the electron cloud surrounding the positive ion core. So you see, when you have applied force during the deformation, the atom is easily to slide on top of one another.